Hey guys. So now that you have your car working and it's moving 5 meters, it's time to take some performance graphs so that you can see how well it's doing and show how it converts energy. So to do that, we're going to start by taking a look at the car moving. So first, I took my car and I ran it through a 5 meter long run. I marked the ground. And you can kind of see here, this was a student from a previous year. They videotaped the car running 5 meters from above so that they could see where it's going all the time. Check it out. There it goes. Perfect. Okay, and they've even got it in slow motion here. So when they did that, what we did was we took the time when it started, and then every time it hit a meter mark, which was marked out on the floor, so we measured out 5 meters and marked it with a piece of tape on the floor. Every time it hit that meter mark, we hit split so that we got a time. So like time for the first meter, second meter, third meter, fourth meter, etc., all the way to the end. All right. After looking at that, we were able to go in, and take a look at this spreadsheet. So we created the spreadsheet and we started by doing distance. So I marked out my distance first, 0, 1, 2, 3, 4, 5 meters. And then from the distance, I marked out the time. Let's see if I can zoom this in at all. Nope. So I marked the time and how long it took to get to every meter. And it was 1.3 seconds for the first meter, 2.4 when it hit the second meter, 3.1 when it hit the third meter. So this is the running time, right? This isn't the difference between the times. It's the full running time all the way through. So now I've got my time and I've got my distance. Now I'm going to make another set to do time versus velocity so that I can see how fast it was going at different points. For that one, what I'm going to take a look at is right before and after each meter mark. So on here, I happen to know that when I run this car along this floor, each of these tiles is exactly 1/3 of a meter. So when I mark right back here and I see that the car goes to there, I would start my timer. And then when it gets to here, I would stop my timer. So in total, that's a distance of 1/3 of a meter plus 1/3 of a meter is 2/3 of a meter. So 1/3 of a meter before to 1/3 of the meter after. If you want to use a different distance and mark out before and after your meter marks, that's fine. You could use 0.2 meters, like 20 centimeters before and 20 centimeters after for a total distance of 40 centimeters. My tiles are just exactly 1/3 of a meter. So I used 1/3 of a meter before and 1/3 of a meter after. Total distance is 2/3 of a meter. Now, the reason that I used before and after is because that gives me the average right at the meter mark, right? I've got a little bit before, a little bit after. Their middle is going to be on that meter mark. So that gives me a rough estimate of what the speed would be right as it went over the meter. Okay, so that gives me some velocities. And the way that I figure out those velocities is by going back to my spreadsheet. Oops. Can I get out of this video? Please stop being large. Video. Escape. There we go. So here we go. Now we're back on, and now I can do my velocity, which is equal to my change of distance over my change of time. So for this section, at the second meter mark, I found that it was 2/3 of a meter, 0.67 meters, divided by the amount of time that it took to go there was 0.8 seconds. So I put that in, I did equals 0.67 divided by 0.8, and that gave me a value of 0.8375 meters per second. So that gave me all of my values for velocities. Now I've got time versus velocity, and I could graph that. And then finally, it was time for me to do my energies. So I'm going to do potential energy, kinetic energy, total energy, and thermal energy. Since I know that potential energy is 1/2 kx squared for spring potential energy, and this one was running off of a rat trap, so that's a spring, I figured out the spring constant, and then I figured out how much that spring had stretched. And I put that in for the equation. So I did equals, my distance was 0.6 meters, times my spring constant was 20 newtons per meter, and then 1/2 of that, so divided by 2, right? Instead of doing divided by 2, I could also do times 0.5. Either way works. So it was 1/2 kx squared, and that gives me my potential energy. My kinetic energy at the very beginning, it wasn't moving, so that would be 0. I could also do an equation. So kinetic energy is 1/2 mv squared in this box here. So if I take 1/2 0.5, divided by 2, times the mass of the car was 1/2 of a kilogram, so 0.5 kilograms, times C13 times C13. Well, C13 is the velocity at time 0. So it's taking the velocity there times itself twice. So I use that same equation by copying it and then pasting it down below all the way through for all of my other kinetic energies. So there you go. For this one, for my potential energy, my spring potential energies, for each additional one, I saw that it kind of went down, and then by meter 3, it was all the way done, right? It had snapped, and so there was no potential energy left. So at that point, I went down to 0. For these intermediate ones, I said it was 0.4 meters long, 0.6 meters long, then 0.4, then 0.2. My total energy is going to be equal to my initial potential energy, my maximum potential energy. So that was 3.6. So I just made 3.6 all the way down, right? That equals F3, which is my potential energy at that point. And then finally, for thermal energy, my thermal energy is going to equal to my total minus, so here I'll show you how that works. It's going to equal my total energy minus my potential minus my kinetic. So it's, in this case, H4 minus G4 minus F4. So it takes my original total minus all the other types of energy, and that gives me how much has been lost to heat. So I've got all of these guys graphed. Next, I can highlight them and throw them in a graph. So if I do that, I'll do just the energy one. Highlight, insert, chart. And it'll very slowly make me a chart. And boy, that looks funky, doesn't it? So it's made me a scatter chart, and that is not the kind of graph that I want. I want it to be a line graph. So I'm going to choose from here a line graph. And that looks a little bit better. Now it's at least got the lines on it. The x-axis is time. Potential, kinetic, total, and thermal energy are the other lines, which is good. And I know that I've done it right because my total energy stays the same. My thermal energy, green, gets bigger. My potential energy goes down and gets smaller. And then my kinetic energy stays relatively low the whole time, but goes up and down just a little bit. So that looks pretty good. However, I'm not totally happy with it. I also want to customize it just a little bit and change some of the titles. So in here, the chart title right now, I'm just going to call this like energy versus time. Oops. For my car. And then I've got the key there, which is nice. And I also want to put in some horizontal axis. That was the time in seconds. Good. Perfect. Oh yeah, look at that. And then the vertical axis, I'm going to call, that one is energy measured in joules. So I'll put in a title there. And now it looks pretty nice, right? That chart is pretty much the way that I want it to be. Cool. So there's one issue with this chart. And that issue is that right here where the thermal energy goes down, once energy is turned into heat, I can't make it not heat anymore. I can't switch it back and turn the heat into speed. because of entropy, energy should always go to a more disordered form. And heat is like the least disordered form of energy that we're dealing with here. So I shouldn't have this little downward spot. What that probably means is that I've mismeasured my velocity right there, because my kinetic energy has a really big spike at meter 3, which seems unlikely and unusual. So I think I might have mismeasured my velocity. I might have to go back and check that and smooth that out. And if I did that, the cool thing about a spreadsheet is I can move my graph around and I can change the velocity, and that'll change everything else. So at 3, I thought there was an issue with my velocity. It was 0.67 over 0.32. Maybe I mismeasured that. Maybe it was actually 0.52 seconds. So that would change that. And now all of a sudden, it has changed my velocity. And then when it changed my velocity, it also changed my kinetic energy at 3 meters, which was 3.1 seconds. And then it also changed my total energy, and it changed, or no, it didn't change my total energy, but it did change my thermal. And now you can see on the graph, whoops, it looks a lot smoother. Now it doesn't have that kick down, and this looks totally appropriate and right. Okay, so now my energy graph looks really good. So just as a general rule, your energy graph should look something like this. Potential goes down, kinetic goes up, or sorry, kinetic stays low, relatively low. Thermal goes up, and total is a flat line at the top that's the same as your original potential in most cases. All right. Just so you can see, I've also graphed some other stuff here. I've graphed my distance versus time, showing that it goes further the longer I go along. I've graphed my time and velocity. So it shows that it goes faster, 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 and then slows down at the end and comes to a stop, right? It comes down and breaks at the very end. So that's another thing, is that at the very end, at 5 meters, I have come to a stop. My velocity is back down to 0 at the end because I stopped at 5 meters. Cool. So that's an example of how you could set up for that graph. I will share this document with you as well so that you can take a look at what the equations are and work from there. Awesome. Enjoy doing some performance graphing.